Hello, this is Lucia with the Nevada Division of Minerals, and thank you for tuning in to listen to this talk titled, All That Glitters is Not Just Gold, Critical Minerals in Nevada. This is the general presentation outline. We will review the definition of critical minerals in Nevada, critical minerals at the global scale, and critical mineral activity in Nevada. We will conclude with a quick review of some online data resources. What is the definition of a critical mineral? A critical mineral is a mineral that has been 1. Identified to be a non-fuel mineral or mineral material essential to the economic and national security of the United States, 2. From a supply chain that is vulnerable to disruption, and 3. That serves an essential function in the manufacturing of a product, the absence of which would have substantial consequences for the U.S. economy or national security. On February 24, 2022, the current list of critical minerals was published in the Federal Register. Of the 50 critical minerals listed, Nevada contains known occurrences or deposits of 33 of the 50 minerals which are shown on this screen. Documented occurrences in Nevada are underlined and in bold, and those with past production are signified with an asterisk. Critical minerals occur in more than 81% of Nevada's historic mining districts, some more commonly than others, and several historic mining districts have more than one documented critical mineral occurrence or deposit. Minerals that are lucky enough to land themselves on the list of critical minerals must each be scrutinized independently of one another. There are many questions that need to be addressed, such as, what is the economic vulnerability of the individual mineral? How geographically concentrated is the source of each mineral? What is the disruption potential? What is the foreign ownership of the mineral assets and operations, including processing facilities, and so forth? Each commodity and form of that commodity utilized must be evaluated in detail, and where supply chains are convoluted, this may be a difficult task. Also, without a functioning crystal ball, it is hard to see what technologies may emerge in the future which could impact supply and demand, hence the reason for an ever-evolving list of critical minerals. I would like to touch on data sources right now instead of at the end. Starting with the next slide, we will be viewing a series of maps which show some pertinent information for each of the critical minerals that have known occurrences or deposits in Nevada. The data for the following series of maps were obtained from the USGS and the Fraser Institute's annual survey of mining companies. While some of the USGS data is dated, these data sets are the only global representation of commodities such as arsenic, bismuth, fluorspar, magnesium, and tungsten, which were not addressed in the 2017 USGS report on critical mineral resources of the U.S. Therefore, they were not included in the 2017 Critical Global Minerals dataset, which is also included in the maps we will see shortly. The Critical Minerals dataset has not been updated to reflect the current list. In all maps, all 4 layers shown here in yellow have been utilized unless the data for a given commodity wasn't available. Keep the vintage of the data in mind if something you know to exist is missing. As of September of last year, the USGS was working on updating these data sets and anticipated this year to be a big data publishing year, but the data is not available just yet. Each of the maps we will review will look like this. The glowing dots on each map represent U.S. mines and plants, mineral operations outside the U.S., major mineral deposits of the world, and global critical mineral deposits, mines, districts, and mineral regions. Countries, states, and provinces are color-coded according to their investment attractiveness ranking in the 2021 Fraser Institute's annual survey of mining companies, red being the highest-ranking jurisdictions and yellow being the lowest. Those regions lacking color either did not respond or did not provide enough data to be evaluated in the survey. The countries that are import sources for the U.S. for the highlighted commodity are outlined in white. Each slide supplies a list of commodity forms considered critical, a summary of domestic mining and secondary production from 2017 to 2021, the top producing countries from 2007 to 2018, import sources from 2017 to 2020, alternative supply options, and major commodity uses. In the upper right-hand corner, it is specified whether the commodity is predominantly produced as a byproduct and what host commodity it is a byproduct of. In the bottom right-hand corner of each slide is the U.S. 5-year net import reliance calculated from figures presented in the 2022 USGS Mineral Commodities Summaries. Import reliance refers to the reliance on foreign sources for raw and processed mineral materials. Rolling in alphabetical order, we will start with aluminum. Aluminum is used in transportation applications, packaging foils, building materials, electrical consumer durables, and machinery. A small fraction of aluminum consumed has been mined domestically in the last 5 years. Secondary aluminum production is entirely reliant on imported bauxite. Domestic recycling provides a steady supply of aluminum to the U.S. The U.S. 5-year average net import reliance for aluminum is 48%. The top producing country for alumina and aluminum is China, and the top producing country for bauxite is Australia. Import sources are listed in this screen. Some alternative supply options for aluminum include diversifying import sources and increased recycling. Antimony is used to manufacture several items, including lead-acid batteries, like the ones found in many vehicles, backup power facilities for cell phone towers, hospitals, and standalone power systems, ammunition, lead alloys, ceramics, glass, and rubber products. It is also used as a flame retardant in items like mattresses, workwear, and textiles. Some mining has taken place in the last 10 years, but no mining was reported in the U.S. for 2021. There is one metal producer here in the U.S. who is totally reliant on imported feedstock. The U.S. 5-year average net import reliance for antimony is 83%. China is the leading global producer of antimony. We import from several regions of the world, which are all listed here on this screen. Some alternative supply options for antimony include recycling and further research on deposit models to further assist in exploration. Arsenic is mainly used as a wood preservative and for the production of pesticides, herbicides, and insecticides. As a metal, arsenic is used to make alloys and semiconductors. Semiconductors control the flow of current in electronic devices and equipment and are used in integrated circuits, telecommunications, solar cells, and special optical materials. Recovery of arsenic in the U.S. is generally not economical, so it is mostly discarded, resulting in a 100% net import reliance. China is the leading producer of arsenic. China, Japan, Morocco, and Belgium are the main sources of U.S. imports. There is very limited recycling of scrap. Some supply options include more recycling of scrap, recovery of arsenic from smelter residues, and the development of new processing methods which could make domestic extraction economical. Barite. One of the main applications of barite is as a weighting agent and filler in drilling fluids, which are used in mineral exploration, oil and gas, and geothermal borehole or well drilling. Barite is also used to manufacture rubber, plastics, paints, and glass. Barite production fluctuates globally, mainly due to fluctuations in the oil and gas industry, but China is the leading producing country. There is limited domestic production of barite, which only meets a small fraction of total U.S. demand. Net import reliance is 82%. Substitution, deposit model research, and new processing methods are options put forth to reduce foreign reliance. Beryllium. Beryllium is crucial for defense applications such as radar, telecommunications satellites, infrared target acquisition systems, surveillance systems, and electronic countermeasures systems. It is also used as an alloy for underwater pressure vessels, telecommunications, electronic connectors, shielding, and aircraft landing gear. The U.S. is the leading producer of beryllium, but production of this crucial commodity is from a single mining company in Utah. Net import reliance is calculated by taking imports and subtracting the exports, then making adjustments for government and industry stock changes, which, in the case of beryllium, leaves the U.S. 14% net import reliant. Minor domestic recycling is taking place. During the last 10 to 15 years, U.S. production has remained consistent, where Chinese production has doubled. Options for securing beryllium supply include developing assessment models for new deposits and more efficient extraction methodologies. On to bismuth. Owing to its antimicrobial properties, bismuth is largely used in the pharmaceutical industry to treat stomach ulcers, burns, intestinal disorders, and acid reflux. Bismuth is also used as a lead substitute in plumbing applications, and smaller amounts are used to make ceramic glazes, crystalware, semiconductors, and triggering mechanisms for fire sprinklers. Bismuth is contained in lead ores mined domestically. These ores are shipped and processed outside of the U.S. Recycling accounts for less than 10% of U.S. consumption. China is the top producing country, providing over half of the world's processed bismuth. The average net import reliance for bismuth comes to 94%. The U.S. relies on China, Korea, Mexico, and Belgium for imports. More recycling and increasing the recovery rates from lead ores could help to maintain domestic bismuth supplies. Chromium. Chromium is used to manufacture stainless steel, heat-resisting steel, pigments, and synthetic gemstones. It is also used in other high-temperature applications, leather tanning, along with wood preservation. There is no domestic production of chromium, but recycling satisfies a fraction of domestic demand. South Africa is the leading producer of chromium. Ferrochromium and chromium metal are largely sourced from South Africa and Russia, respectively. The average net import reliance for chromium comes to 75%. The U.S. relies on South Africa, Russia, the United Kingdom, Canada, France, and China for imports. Diversifying chromite sources, enhanced processing methods, and more recycling could help to boost and maintain domestic chromium supplies. Cobalt. Cobalt is used to make batteries for electronic devices and electric vehicles. It is also used to make superalloys, which are then utilized in magnets, steels, chemicals, and turbines, like those which generate power from geothermal plants, nuclear power plants, wind farms, and natural gas plants. One active mine in Michigan and mine tailings from Missouri produce cobalt-bearing concentrates. These concentrates are exported internationally for processing elsewhere. Recycling of scrap significantly contributes to U.S. supplies, lowering the average net import reliance to 73%. The Democratic Republic of the Congo is the largest global source of cobalt, though China dominates refinery production. Import sources of cobalt to the U.S. are listed in this screen. Supply options include recycling, better geologic models to assist in the exploration for new deposits, and new methods which would increase recovery and processing. Next up, fluorspar. Fluorspar is used to produce many common materials that we use every day, like aluminum, steel, glass, and cement. Fluorspar is also used to manufacture chemicals such as fluorocarbons and fluoropolymers. Fluorocarbons are used in cooling systems, heat pumps, and fire suppression. Fluoropolymers are utilized in the manufacturing of laptops, cell phones, satellites, fiber optics, lightweight vehicles, and much more. Metallurgical grade fluorspar is mined domestically in limited quantities, but there is no mining for acid grade fluorspar, and there is also no recycling. The U.S. is 100% reliant on fluorspar imports, most of which come from Mexico. Vietnam, China, Canada, and South Africa are secondary import sources. China is the leading producing country, accounting for over 50% of the global supply. Domestic supply options include possible extraction from brines and emphasis on discovering new conformable fluorspar deposits. Gallium. Gallium is crucial to the functionality of many electronic applications, like the computer or electronic device that you are using to view this video, along with cell phones, microwave circuits, infrared circuits, light-emitting diodes or LEDs, and diode lasers. There is no domestic mining of gallium, though we do refine imported crude gallium, making the U.S. 100% reliant on imports. China is the top country for gallium production and is the main source of U.S. imports. Secondary sources include Canada, the United Kingdom, Japan, Ukraine, and Germany. Options to meet consumptive demands include research to understand future impacts on supply, the development of improved assessment models, new and more efficient extraction and recycling technologies, along with more domestic refining and recycling. Graphite. The use of graphite has become more and more important as it is employed to manufacture essential parts in energy technologies such as fuel cells, battery anodes, pebble bed nuclear reactors, and solar cells. Electrodes, refractories, and foundries are also major graphite consumers. While there has been no recent mining of graphite in the U.S., there are some resources currently in development. There is domestic recycling of refractory graphite. The U.S. is 100% reliant on imports. China mines 75% of the world's natural graphite and has some of the world's largest resources. China, Mexico, Canada, and India are all import sources for natural graphite in the U.S. Options to aid in domestic supply include exploration, further research into the occurrence and distribution of high-grade flake graphite deposits, and more recycling of refractory graphite. Moving on to indium. Indium is utilized for electrical conductivity purposes in items like flat-screen TVs and in alloys, compounds, semiconductors, electrical components, and solders. There is no domestic mining of indium, though several companies here in the U.S. use imported materials to produce indium products. The U.S. is 100% reliant on imports. Over 2/3 of the world's indium is refined in China and the Republic of Korea, though China is the leader in production. China, Mexico, Canada, the Republic of Korea, and France are all import sources for indium to the U.S. Options to aid in domestic supply include refining of indium contained in zinc ores and the development of recycling processes. Lithium. Lithium has high electrochemical potential, meaning its ability to store chemical energy, which can be converted to electricity, is high, and this is why it is used to make rechargeable batteries. Lithium is also used in ceramics and glass to raise the melting temperature and in lubricating greases. Here in the U.S., there is one producing mine and two producers of lithium compounds, along with domestic recycling of lithium-ion batteries. Manufacturing of key lithium compounds used in lithium-ion batteries is concentrated outside the U.S., mostly in China. Australia is the leading country for lithium mining, and China is the leading country for refining. The U.S. is greater than 40% net import reliant, and what is imported comes from Argentina, Chile, Russia, and Asia. Supply options include further research on deposit models, recycling, and the establishment of the domestic lithium-ion battery supply chain. Magnesium. Magnesium is used in the casting of metal parts, like those used in the manufacturing of automobiles. Magnesium is also used as a fertilizer, for nutritional supplements, for both animals and humans, for wastewater treatment, and in flooring tiles. Domestic production and recycling of magnesium accounts for a large portion of domestic consumption, bringing the U.S. average net import reliance to less than 45%. China is the top producing country for magnesium. Imported magnesium metals come from Canada, Israel, Mexico, South Africa, Russia, and Gabon. In order to maintain or improve domestic supply, actions include expanding domestic resources, improving processing methods, and recycling. Now for manganese. Manganese is mainly used in the manufacturing of steel, but it is also used in some rechargeable lithium-ion batteries, alkaline batteries, and non-rechargeable lithium manganese dioxide batteries. In aerospace and other transportation applications, electrolytic manganese metal is used to make non-ferrous alloys. Imported manganese ore is processed domestically. The U.S. net import reliance figure for manganese is 100%. Electrolytic manganese is only supplied by China and South Africa, who are also the two top producing manganese countries in the world. Manganese ore is imported from several countries, which are all listed on the screen. Options for boosting domestic supply include increasing processing and mining efficiency, along with discovery of local higher grade deposits. Nickel. Nickel is used in alloys, steels, electroplating, catalysts, and chemicals. Nickel ore produced from one mine in Michigan was exported to smelters in Canada and overseas. Some secondary nickel production occurred from a Superfund initiative and as a byproduct of smelting and refining. There is also some recycling for nickel, which is utilized in steel applications. The U.S. 5-year average net import reliance is 50%. Though many countries mine and refine nickel, Indonesia is the leading country for mining nickel ore, and China is the leader for refining. U.S. imports come from Canada, Norway, Finland, and Australia. Options for securing domestic supply include diversifying import sources and further development of recycling processes. The platinum group metals. One major use of the platinum group metals is in catalytic converters to reduce automotive emissions. They are also used in electronics, dentistry, jewelry, petroleum refining, for the manufacturing of medical-grade silicones and antibiotics, for investment purposes, and much more. Platinum and palladium are mined, recovered, and recycled here in the U.S. Other platinum group metals that are mined in the U.S. are sent elsewhere for recovery. The net import reliance for palladium and platinum is 55%. South Africa dominates global production of iridium, platinum, and rhodium, and are important sources for platinum group metals to the U.S. along with Zimbabwe, Canada, Germany, Italy, Switzerland, and the United Kingdom. Supply options for the U.S. to meet increasing demand include further developing the recycling process for recovery of other platinum group metals and further research into platinum group metal formation in other geologic settings. The rare earth elements. There are several applications for the rare earth elements, including glass manufacturing, catalytic converters or emission control on vehicles, oil refining, battery anodes, steel making, computer and cell phone display screen lighting, lasers, nuclear control rods which control the rate of fission, synthetic gems, fertilizers and magnets such as those used on hard disk drives or in magnetic motors in cordless tools, wind turbines, speakers or headphones, MRI scanners, fishing reels, and much more. Domestic production comes from the Mountain Pass mine in California, but all ores are exported for processing. Other rare earth element projects are undergoing development. Limited recycling of batteries, permanent magnets, and fluorescent lamps is a minor domestic source for rare earth elements. The U.S. is 100% reliant on imports. China dominates the mining and processing of rare earth elements globally. Rare earth element compounds and metals are imported to the U.S. from China, Estonia, Japan, and Malaysia. Options to boost domestic supply and decrease foreign reliance include diversifying production, reducing waste, developing substitutes, increase recycling, develop economic extraction methods, and continued research to enhance deposit model understanding. Tantalum. Tantalum is used for alloys to manufacture capacitors like those found in electronics, mobile phones, and personal computers, to make carbides for cutting and boring tools, and for making glass lenses for lighter weight cameras. There is no domestic mining of tantalum. There is some domestic production of alloys, capacitors, carbides, and compounds from imported sources, making the U.S. 100% reliant on foreign materials. There is some recycling and processing of scrap. The top global country for tantalum production is the Congo. The U.S. imports from several countries, which are all listed here on this screen. Some options to secure domestic supply are to expand domestic recycling, and since known domestic deposits are low grade and mineralogically complex, discovery of higher grade deposits is also a priority. Tellurium. Tellurium is used to manufacture solar photovoltaic cells, which convert light energy into electricity. Tellurium is also used as additives to copper and lead alloys, in thermoelectric devices, in cast iron, and in the production of rubber. Some tellurium metal is mined with copper and is recovered during refining. There is very limited recycling in the U.S., leaving the average net import reliance greater than 95%. China leads global production of tellurium. Most tellurium is imported from Canada, China, Germany, and the Philippines. According to the USGS, in the near future, recovery of lower copper grades may force recovery of oxidized copper ores by solvent extraction. In this process, it is not possible to recover the tellurium as a byproduct, as is possible through the smelting of higher grade copper sulfide concentrates. This change in method could potentially lead to a greater emphasis on precious metal deposits to meet global and domestic tellurium demands. Future research may focus on methods to recover tellurium from two new sources, one being the extraction of tellurium from iron manganese crusts on the ocean floor, and the second being the reprocessing of old waste piles. Next up, tin. Tin is used to manufacture chemicals, tin plate, alloys, solder, babbitt, brass and bronze, tinning, and bar tin. There is no domestic mining of tin, but there is tin production from old and new scrap. China is the top tin producer for both mining and smelting. U.S. imports come from Indonesia, Peru, Malaysia, and Bolivia. Some options for securing tin supply include securing substitutions, export reductions, stockpiling, higher grade resource identification, or recovery from ore bodies where other profitable commodities are present. Titanium. Titanium is used as a pigment in paints, as a catalyst, in ceramics, in textiles, and due to its strength and corrosion resistance, it is used in aerospace as well as in steel production. All forms of titanium deemed critical are produced domestically, and titanium scrap is imported for secondary production of titanium and titanium dioxide. The 5-year average net import reliance for mineral concentrates is 91%. Australia is the leading producer of mineral concentrate, and China is the leading producer of sponge. Sources for titanium come from several regions listed here on the screen. Options to maintain or increase domestic titanium supplies include the development of cost-effective extraction methods from various materials and update the current ore deposit model. Tungsten. Tungsten is used to make alloys or superalloys, which are then used in a variety of applications, including aerospace, jet engines, satellites, helicopter rotor blades, and land-based turbines. Owing to its durability, tungsten carbide is used to manufacture munitions, wear-resistant tools, and oil and gas drilling equipment. Tungsten is used to make lighting and specialty filaments, which must have the ability to withstand high temperatures. Domestic commercial production of tungsten has not taken place since 2015. There is some recycling and significant processing of imported ores and concentrates. Our net import reliance sits at greater than 50%. China leads global production for all forms of tungsten and is who we source much of our tungsten from. The U.S. also imports tungsten from European Union countries, Bolivia, Germany, Austria, Canada, and Vietnam. Increasing domestic recycling would assist in maintaining supply. Vanadium. Vanadium is used to make alloys, which are then employed to make things like power-generating turbines and blades for jet engines. It is also used to manufacture batteries for large-scale electrical storage, to manufacture rubber for petroleum cracking, and in the manufacturing of sulfuric acid, which in turn is used to produce a large variety of items that we use every day, such as fertilizers, detergents, paints and pigments, plastics, fibers, rayon, paper, batteries, explosives, and pesticides. There has been sporadic domestic mining of vanadium and some recycling. The average 5-year net import reliance is 99%. China produces over half of the world's mined vanadium. Austria has been the most important import source for ferrovanadium and Brazil for vanadium pentoxide. Russia, Japan, Taiwan, and South Africa are also import sources for the U.S. Options for maintaining supply include the optimization of extraction methods and increased recycling. Zinc. Zinc is used for galvanizing, brass and bronze sculptures, zinc-based alloys, and vitamins. Zinc is mined in 5 states from 7 mining operations. There is a significant amount of refined zinc recovered from secondary materials. The net import reliance for zinc is 83%. China is the top producing country for mining and smelting of zinc. Options to secure domestic supply include expansion of current mining operations along with refinery and recycling capacities. The last critical mineral we will discuss is zirconium. Zirconium is used to make ceramics, foundry sand, opacifiers, refractories, abrasives, metal alloys, chemicals, and as welding rod coatings. There is some domestic production of zirconium, which is recovered as co-products from reprocessing of tailings. There is some zirconium production from recycling of scrap, foundry mold cores, and spent or rejected zirconia refractories. The U.S. 5-year net import reliance is 48%. Australia is the top producer of zirconium. U.S. import sources include South Africa, Senegal, Australia, Russia, China, Germany, and Belgium. An option to secure zirconium supply is to define more cost-effective ways to produce various zirconium forms. In an attempt to see where Nevada stood as far as importance in all of this critical mineral buzz, we used the Investment Attractiveness Ranking from the 2021 Fraser Institute's Annual Survey of Mining Companies, took the 10 highest ranking jurisdictions, and tallied up the mines, deposits, and plants for each critical mineral we just discussed. Again, only using the USGS data outlined in the 7th slide. If we look at the count for the number of critical minerals that occur in each jurisdiction per acre, normalized, Nevada comes in first, followed by Idaho and Arizona. If we look at the number of critical mineral deposits, mines, and plants per acre, normalized, that occur within the top 10 jurisdictions, Nevada again comes in first, followed by Idaho and Morocco. Bottom line, Nevada appears to be a good place to be exploring for critical minerals. So with that, let's bring our focus back to Nevada and review a little bit about critical mineral activity in the state, work involving critical minerals from government and state agencies, and conclude with some online data resources. Since 1981, there have been no fewer than 323 notices filed with the BLM, with the commodity of interest being one of the critical minerals identified in the 2022 Federal Register list. Keep in mind, the commodity of interest isn't always specified, so no fewer seems like a pretty accurate statement. Currently, there are 33 of these notices whose disposition is authorized or pending. The claimants and/or operators of these authorized notices are listed in the table shown on the right. Since 1981, there have been no fewer than 43 mine or exploration plans filed with the BLM, with the commodity of interest being one of the critical minerals from the 2022 Federal Register list. Again, the commodity of interest is not always or has not always been disclosed. Currently, there are 26 of these plans whose disposition is authorized or pending. The claimants and/or operators of these authorized plans are listed in the table shown on the right. At the state and federal government level, there are two large projects in progress that pertain to critical minerals. The first is the Geoscience Data Acquisition of Western Nevada Project, or Geodon. Several agencies, both federal and state, are participating in this project that focuses on conducting airborne geophysical and 3-depth or three-dimensional elevation program LiDAR surveys over Nevada and California in an effort to collect information on undiscovered geothermal, critical mineral, and groundwater resources in the Western Great Basin and the Walker Lane region. There has been a $10 million investment in Nevada to meet the project goals, which has many benefits as highlighted on the screen. The Nevada Bureau of Mines and Geology is actively involved in this project. The second project involving critical minerals at the state and federal government level is the Earth Mapping Resources Initiative, or Earth MRI. The goal of this project is to improve knowledge of the geologic framework to identify areas with potential to contain undiscovered critical mineral resources and to decrease the nation's reliance on foreign resources of minerals critical to our security and economy. This project consists of a partnership between USGS, state, and other federal agencies. There are 2 ongoing projects and 2 documented future projects that the Nevada Bureau of Mines and Geology will be participating in. The 2 ongoing projects are the Mountain Pass and Clayton Valley or Rhyolite Ridge projects. The 2 future projects will be in the Humboldt Complex and in the McDermott area. Moving on to data resources. First stop, Mr. Data, the USGS Mineral Resource Online Spatial Data Site. This is the source for most of the geospatial data shown in this presentation. There is a variety of great geospatial data that is possibly dated but free to use here. Types of data include mineral resource, geological, geochemical, geophysical, and geochronological data, all of which are downloadable. Here at the Division of Minerals, we have put together some web maps that focus on critical minerals. To access the content, scroll down to the Pages Listing section on the homepage of our Open Data site and click on the Nevada Mineral Producers, Commodities, and Occurrences page. If you scroll down towards the bottom of this page, you will come to the Critical Minerals section, where you will not only find this video, but also a video tutorial for the web applications we are about to review, 2 interactive web maps, and the colorful mining districts map shown earlier in this presentation. This is the first web map you will come to. This map contains historic mining claim listings, notices, and plans, along with Tingley's historic mining district data, which has been filtered to display those mining districts with critical mineral occurrences or deposits. And of course, all maps are interactive and have pop-ups, which will give more information on the features presented within. If you scroll down on the page, you will come to another web map, which will compare current and historic data with respect to mining districts known to contain deposits or occurrences of critical minerals. When we zoom in on this particular map, current mining claim point listings, mining claims per section, major mines, and authorized or pending notices and plans render in the map panel to the left. In the right-hand map panel, historic mining claim point listings and any notices that are closed, canceled, or expired are displayed. Map extents will always mirror one another. The legend can be displayed by clicking the double arrows outlined in blue in the upper right-hand corner of the map panels. The information box can be minimized by clicking the double arrow to the right of the box, which is outlined in red. We will click on some points within the map, and you can see our familiar pop-ups appear. Unfortunately, viewing mass amounts of data in this application is a bit cumbersome, as one cannot view the data in an attribute table. For the option to view attribute tables and for more general functionality, the map we previously discussed is recommended. But this comparative map is great for looking at a lot of data on one screen. The pop-up can be toggled into a list view by clicking on the number of records selected in the bottom right-hand corner of the pop-up, which is outlined in blue. Don't forget about the Nevada Mineral Explorer, which is a web application developed by the Nevada Bureau of Mines and Geology and the Nevada Division of Minerals as a tool for explorationists to identify and discover mineral resources throughout Nevada. This application was created to be a one-stop shop for explorers to view and interact with data relevant to Nevada geology, mining, precious metals, industrial minerals, geothermal resources, along with oil and gas. Data has been gathered from various sources, including the Nevada Division of Minerals, the Bureau of Mines and Geology, the USGS, the BLM, and the Forest Service. There are two more items I would like to present. The first is the Claims Residency Map Experience web application, or the CRIME map. This application is new and was developed in order to highlight areas that have had significant exploration interest. There are 3 heat maps presented in the application, one which shows the density of claims per section over time, and the other 2 show the sum and average of annual assessment and/or maintenance fees paid per section over time. All 5 million points used to create this grid are available to interact with in the map, along with current, active, filed, or submitted claims from the BLM's MLRS database and all notices and plans from the BLM's LR2000 database. Points from the USGS MERDS and Mineral Deposits database are also available in the map and linked directly to the USGS Online Mineral Resource Data System. Data from the Nevada Division of Minerals Open Data Site and the Claims Hub site have been aggregated into this one application to represent the Western U.S. The CRIME web map application can be found on the main pages of the Nevada Division of Minerals Open Data Site and the Claims Hub site. We will remain on this slide and finish the demonstration for the application. The demo has no audio. The second item is the Claims Hub site. The Claims Hub site is a platform for exploring and downloading mining claims, plan, and notice GIS data. Unpatented mining claims, plans, and notices are presented in interactive web applications on a per-section basis for Arizona, California, Colorado, Idaho, Montana, Nevada, New Mexico, Oregon, Utah, Washington, and Wyoming. The URL and QR code for the claims website are shown in this screen. And we have come to the end of this presentation on critical minerals. I would like to thank you for tuning in, and I hope that you have a great day.